Okay, so the plan for today is to cover section 16.2 and uh, start on section 16.3. I don't think well, I know we won't get all the way through 16.3. Um, I'm hoping that we get through our discussion on kind of conservative vector fields, and then maybe leave a few examples for a supplement tomorrow. So I'm hoping to get a decent bit of the way through 16.3 today, get kind of hit the really high points, and then maybe talk about some side notes, some applications, some examples in a shorter supplement, maybe under an hour or so, and then also discuss Green's theorem in a separate supplement. So that is the plan for the rest of the week, and that'll bring us to section 16.4. And the plan for today is to start with line integrals. And 16.2 might be a little bit of a deceptive section because there's just a lot in this section. There are a lot of different ideas. We have scalar versus vector line integrals. We have some different applications and so on. Some physics applications come into play. So there's really kind of a lot of material in 16.2. But I think once you get the hang of it, the kind of practical side of things is pretty straightforward. So I think you'll see that actually procedurally doing the work usually isn't all that bad once you kind of get your head wrapped around all of these different concepts that are being introduced here. Okay, so we are going to discuss line integrals. So a type of integral in maybe something like three-dimensional space in the case that we're going to look at next. But before we do that, let's just kind of remember how just kind of standard integration works. We have x and y. We have a function y equals f of x, and we're going from a to b. And of course, lots of applications of integration, but the kind of most standard application is finding the area under the curve. So in other words, if I had a kind of flat wall, the xy plane, if I was looking at my floor, the x-axis, between A and B, say two vertical lines, and then I had some kind of curvy top to my wall, I might ask something like, how much paint do I need to paint this flat wall with three flat sides and a curvy top? And this gives me an idea of how much paint I might need, right? If a gallon of paint covers a certain number of square feet on a typical application thickness. So that's the idea of a regular, so to speak, integral. And of course, we have our good old idea of making a bunch of Riemann boxes of width delta x, setting their height to be more or less f of x at some anchor point taken in that interval, adding up those boxes, taking a limit. That same kind of idea should be pretty familiar now from a lot of different contexts. Okay, so what is a line integral then? Well, here let's consider a function z equals f of x comma y. And this particular function that I'm showing here is just x times y. It's kind of complicated enough that it's not super boring, but it's simple enough that we can pretty easily tell what's going on. And I have two different perspectives here. One looking from kind of this direction. Here we have the positive y-axis and the positive x-axis. So we're looking kind of at a 45 or so degree angle from what we might typically think of looking at it, 45 degrees from square. And then down here I have, again, positive x-axis, positive y-axis, just looking at it slightly rotated so that we can get a little bit more of an idea of what this looks like. Now, I still want to have this sense, in a sense, of kind of how much paint is it going to take me to paint this wall. So when I look at a line integral in 3 dimensions, what I'm thinking of is I'm thinking of a path in the xy plane. So a curve maybe that looks like this, or maybe that looks like if I kind of draw it and you imagine it in the XY plane below the red function, might look like that. I can pick some different path. I mean, I suppose I could pick a straight line as well if I wanted to. But if I pick a path that looks like a little piece of a circle like this, on this up here, it might look something like that. Now, of course, if I took a straight line instead, I could imagine that at each point along the straight line, I have an associated height of my curve. Maybe I'll draw it in blue, maybe something like this. Oh, I went a little bit too far above the curve there. But again, in my one that's trying to be too helpful here. There we go. Again, if I took a path that was a straight line, I could kind of pull this out to the side here, and this would look more or less like just my standard old integral up here. Now, of course, the straight line is not, one of the axes, so it won't be exactly the same as up there, but it would look pretty similar. Sorry for the jumping around. I'm just erasing all of the straight line stuff. Okay. But really the interesting thing about line integrals is I could pick a straight line path in the XY plane and look at that function, but I also could pick a curved path. Let me actually draw this curve a little bit further out so I can illustrate a little better. So I could pick a curved path in the XY plane. I could pick this or some other path, whatever path I would like. And that path is going to kind of act like my independent variable axis up here. It's going to act as kind of the floor. So I could imagine instead of being in a room with a flat wall with flat vertical sides and a flat floor, now I'm in a room with what has a flat floor, but it has kind of a curved shape to it. And then I look at this wall and I see that, say above this point, I might be here on my surface, and above this point, I might be here. And I kind of have this tracing of my surface. Again, excuse my poor artistry here. My little graph should not be floating above the surface. And I can imagine that this wall here this wall is kind of curved around in the horizontal direction and also has a curvy top to it. So what I've kind of done is I've taken this picture up here and I've kind of taken the x-axis, I grabbed both ends and just kind of bent them so that the curve curves around now. So I'm kind of curving in the horizontal direction as well as in the vertical direction. But this still has the basic feeling of a single integral, right? Because I have like one component of area that's being added up. I have, one direction of Riemann boxes to consider just as I move along this path. So that's kind of what I'm looking at here. I'm asking for this wall that is now kind of curvy in the horizontal direction. It's not a flat wall anymore and also has a curvy top. Something like what is its area or how much paint would I need to paint such a wall? And of course, we have details like if it was negative, we're really kind of talking about signed area, so all those kind of details. But just to get some perspective on what's going on here. Okay, so if f is defined on a smooth curve or path, this green path here, the path we typically call C for curve, and if we're in two input dimensions, the path C might be x equals x of t and y equals y of t. Typically, we want the freedom to choose this path in many different ways. So we think of it as a parametric function, not like a y of x kind of function. We don't want to restrict ourselves that much. And here t is between a and b. Note that this parametric function has an implied direction, right? So we might be traversing this path in this direction. That wouldn't be the same path or the same curve as traversing it in the opposite direction. So we have to be careful about that. This kind of t being between a and b implies a direction. Okay, so if that's true, then the line integral, the integral over c, the integral over the set of inputs c, that's kind of how we would say integral a to b f of x dx. I suppose we could really say integral of a to b like this, f of x dx, integral over the interval a to b. And you can see that that has a very similar feel to integral over our one-dimensional curve c. It's embedded in 2 dimensions, but it's 1 dimension because you can only go, if you're standing there, you can only go forwards or backwards. Integral over our curve f of xy ds. Now, why is it ds and not just like dx or dy or maybe dt or something like that? Well, because up here, my base of my Riemann box is like dx. But down here, when I'm splitting these, this curve and this region into Riemann boxes, I'm taking a chunk, but really the chunk that I'm taking is a chunk of arc length. So by ds, I mean a little chunk of arc length. And I remember that for some smooth curve, I can approximate its length, dx, dy, ds, is approximately ds squared equals dx squared plus dy squared, or ds equals root dx squared plus dy squared. But I don't really know what to do with root dx squared plus dy squared as at the end of my integral. If I just left this as integral over c f of xy root dx squared plus dy squared, what the heck do I do with that? But I do realize that really t is kind of my independent variable here, right? If I think of this f, this is really f of x of t, comma y of t. And ds, this little chunk of arc length, well, this curve is parameterized by t. So I can multiply by dt divided by dt. And if I put this dt on the inside, divide through, I mean, I'm being a little bit flippant here, a little bit hand wavy with all of this. We really should be starting with deltas and moving to d's and so on and moving to derivatives. But roughly speaking, we just pop the dt inside the radical as a 1 over dt squared, distribute, recombine everything under the squareds, and we get the square root of dx by dt squared plus dy by dt squared. That's from that guy coming inside, then times dt. So I'm integrating f times a little arc length unit or arc length factor, and I'm integrating that dt. Note that everything has t as the independent variable here. A couple little notes. First, it's important the curve be traversed exactly once. So for instance, if I was going around a full circle, I would want to make sure that I choose my A and B so that I'm not like mistakenly going around the circle twice or something like that. For like a circle centered at 0 or at the origin, that's usually pretty easy to do, but it can be tricky when we have like a circle centered at like 1, 0 with radius 1. Sometimes when you write those in parametric form, you end up traversing that whole circle on 0 to pi, not 0 to 2 pi. And if you go 0 to 2 pi, you've traversed it twice. So we have to be careful sometimes that we traverse the curve exactly once. But given that the curve is traversed exactly once, the value of the integral doesn't depend on the specific parameterization chosen for the path. So we know there's lots of different parameterizations that can be chosen. And it doesn't matter which one we choose, as long as we're going along the same path and, of course, in the same direction as well. That direction is implicitly part of what we mean when we say the same path or the same curve. Okay, so let's look at some examples. So let's consider the surface f of x equals xy, which is what we have up here, and the path x of t equals cos t, y of t equals sine t, t between 0 and pi over 2, which is what I've drawn up here, more or less. Wasn't being careful with the scaling, but more or less, this is the quarter circle that we're dealing with. We want to compute the line integral of f over the indicated path. That is, compute the integral over c f of xy ds. And then just a little thought experiment. Would you expect to get the same result if c was replaced by negative c? We'll think about that, and then we'll go a little bit further and see if we think that makes sense here. So here's my curve C. When t is 0, x is 1, y is 0. So this is the t equals 0 point. And then when t equals pi over 2, we have 0, 1. Okay, so I need to convert f into a function of t, and I also need to figure out what is this little arc length factor here. Well, let's figure out the arc length factor first. So we need root x prime squared plus y prime squared. I'm just writing these x's and y's with primes because it's clear that they're functions of t, and that's the only thing that we can really mean here. So x prime dx dt is negative sine t. Y prime is cos t. X prime squared plus y prime squared is root sine squared t plus cos squared t is just 1. So in this case, nicely enough, our arc length factor, that radical and all of that, just boils down to just the number 1, and we won't see it coming up in the next step explicitly. But we did go through the work, and it just turns out to be a factor of 1. So I want to integrate f of x y ds. That's going to be the integral from t equals 0 to pi over 2. We're integrating with respect to t. I want to integrate f of xy as xy dt, but of course I don't want to leave f in terms of x and y. I want to substitute in my parameterization. So x times y turns into cos of t times sine of t. This is x times y times 1. This is our square root of stuff, dt. This 1 dt is what ds is. And here I suppose I could use a substitution or a trig identity. This is 1/2 times 2 sine t cos t, or that's sine of 2t. I integrate sine to negative cosine. And then the chain rule would pop out of 2. I need another 1/2 to cancel that, going from 0 to pi over 2. So this is minus 1/4 times cosine of 2 pi over 2 cosine of pi is minus 1. Subtract cosine of 0 is 1. So this gives me negative 2 over negative 4. That's 1/2. So in other words, the area of this poorly drawn shape here, but the area of this kind of shape that curves this way and curves this way is 1/2 for that area. Okay, would we expect to get the same result if C was replaced by negative C? In other words, if we traverse this curve, but in the opposite direction, should we get the same result? Well, I think qualitatively, the answer should be yes, right? If we're finding the area of this wall or whatever, I mean, it doesn't seem like the area should change if I go the other direction. One little note on that is we might actually say, well, wait, doesn't the area change if we go the opposite direction in an integral like this? Don't we have integral a to b f of x dx is negative integral b to a f of x dx? And the answer is kind of yes, but it's because like delta x always goes in one direction, right? The x-axis always is positive this direction and negative this direction. So there's kind of an implied direction here, but ds, a little chunk of arc length, or delta s, it's a little chunk of length that doesn't really have a defined direction. Or in some sense, kind of, if I replace x with negative x up here, then dx turns into negative dx. I guess saying that, you probably should use a different variable because x means two different things the way I said it, but the negative kind of comes through all the way to the front of the integral. But kind of like if I traverse this the other way, like my dx dt and dy dt they're probably going to point in a different direction. Maybe their signs change, but then they're getting squared. So that seems to maybe kill that effect of that changing the direction. And in fact, we can see that if instead of x equals cos t, y equals sine t, this was our curve C, what does our curve negative C look like if I want to start here and go this way on the same curve, but I'm just drawing it off to the side? Well, it turns out that I can use x equals sine t, y equals cosine t. I can kind of see this is going to work because I've just exchanged the roles of x and y, right? I've just flipped everything over the line y equals x, so I get the same curve, but the direction is going the opposite way. But if x is sine t and y is cos t, I mean, that doesn't change my function here. And my root x prime squared plus y prime squared also doesn't change. It's still going to be 1. So in this example, it seems to work out that if I traverse the curve the other way, I get the same answer. Does this happen all the time? Okay, so in example 2, let's look at direction independence of a line integral in a scalar field. A scalar field, we're calling it a scalar field again because this f of xy is a scalar function of two variables. It takes two variables as input, one variable as output. It defines a surface, in this case, a surface in 3 dimensions. 2 inputs, 1 output. So let's suppose that we have a curve C where x is x of t and y is y of t, t going between a and b. If that's a given path, then to traverse that same path in the opposite direction, well, what do I really want? I want, instead of t going from a to b, I want to kind of swap t with negative t. And then to kind of get back to t, I guess, I would have to multiply by -1 And I guess I probably want to add A and B everywhere because I don't want to go from negative something to negative something. So if I add A to everything, I get 0 bigger than or equal to T, bigger than or equal to A minus B. Whoops, A plus T. I added A to everything. And whoops, I wanted to put a negative on everything. I got my negatives a little goofy, but you can see now if we add B, we get a B here, A plus B, and then I'm missing a negative because I just stuck a negative in there. I should have been more careful at the beginning. But the point is that A plus B minus T, when T ranges from A to B, this ranges from B to A. So for A plus B minus T, when T equals A, this is A plus B minus A, this is B. When T equals B, this is A plus B minus B, or A. So probably clear as mud. So, I was just trying to show where I came up with, like why this change traverses the same path in the opposite direction. And that's why. So what's integral of C, integral over C, f of x, y, ds? Well, let's be a little bit clearer now. Now that we have a couple different traversals, this is x of t, y of t, square root of x prime of t squared plus y prime of t squared dt. So that's what we get when we traverse in the, let's say, standard or normal or forward direction. So then integral over minus c of f of x and y ds is going to be the integral. Oh, and I should say up here, integral t equals a to b, because I switched to t midstream there. So integral minus c of f of x, y is going to be the integral f of x of a plus b minus t, y of a plus b minus t, square root of x prime of a plus b minus t squared, plus y prime of a plus b minus t squared, dt, t going from b to a. Those derivatives over there in the x prime and the y prime, they do kind of pop out of -1, but then it gets squared off. So that's what's happening to that minus sign that we might expect to see coming out from something like kind of standard Calc 1, Calc 2 integrals. But that minus that kind of pops out gets squared off whenever we square the x prime and the y prime. And now I'll do a substitution. I'll let u equal a plus b minus t, so du is negative dt. And when t is b, u is a. When t is a, u is b. This is f of x of u, y of u, square root of x prime of u squared plus y prime of u squared, and then minus du. Oh, I've made several dumb errors in this problem. I don't know what my deal is with this problem. I was jumping ahead to the next part, but t goes from a to b still. That's why we did all this business with the a plus b minus t, so that t still went from a to b. So sorry about that. That should be A to B here, then U goes from B to A with a minus. So U equals B to A of this stuff, du, with a minus out in front, and then the minus, which is the order of integration. And we see that integral a to b of f of x of whatever, y of whatever, square root of x prime of whatever squared, plus y prime of whatever squared, d whatever. That's exactly the same thing we have up there. So should have been more careful with my details. I was being a little bit flippant with my negatives and my parameterization there, I suppose. So I always say the Calc 3 is all about bookkeeping and being careful with the details. And then I was trying to get through this too fast and messed up the details. So there's a warning to you that no matter how many times you've done this, if you're flippant with the details and just trying to rush through it, something is going to go wrong. So. Okay, but the point is, though, in a line integral of a scalar field, traversing in the opposite direction, we get the same result. Now, note that if we completely change the path, we would expect to get a different result, right? Because if I completely change the path, and if instead I'm using this path, well, then, of course, the area of my little kind of curvy in many different ways wall, of course, is going to be different. So if I get a completely different path, then I would expect a completely different result. But if I have the same path, but just traversed in the opposite direction, I do, in this case, get the same value for the integral. Okay. So a little bit of notation that will come up in the future that I just want to kind of knock out at this point. We can define our curve in 2 dimensions, 2 input dimensions, as a vector function. Vector r of t equals x of t times I plus y of t times j. Then r prime is just first component x prime, second component y prime, and length r prime, the length of that vector, is square root of dx dt squared plus dy dt squared. So we really see that this whole radical here just really is length of r prime. And the thing we're plugging into f is x comma y, or just vector r. So we could write this in a much more concise notation: integral a to b f of r of t times length r prime of t dt. So sometimes that's a little nicer to write than all of this stuff with the square root and all that. This notation also gives us a little bit of a clue to where we'll be heading when we talk about, instead of scalar functions, what about integrating vector functions? And one other just minor notational note. So we integrated up here in our last example over a curve that went from some point, let's say P, to a point Q. It went from an initial point to a terminal point, and they were not the same point. This is just a curve or a path, but we could have chosen to integrate over some path that was a closed curve. In other words, where the initial point and the terminal point are the same point. So that's what we mean by a closed curve. And you'll often see the notation, an integral sign with a circle, indicating that the curve that we're integrating over is a closed curve. Now, I mean, I suppose if you define the curve alongside the integral, like, somebody should be able to figure out that it's a closed curve, but it's just a nice notation, just as a reminder to make it very clear and explicit that, yeah, this is a closed curve. And we'll see coming up why we might be so interested in knowing that that a certain curve is or is not a closed curve. So that'll come up in the next section. We won't get to that in this lecture, but we should get to that in the supplement. Okay, so let's look at a third example here. Calculate integral over c over some curve, x plus y plus z ds. Where here c, a closed curve, or sorry, a curve, is the helix xyz equals cos t sine t t. Note that we're integrating f of xyz. We're taking three variables as input. We're taking a point in space as the input, and then yielding an output, maybe something like temperature at that point as the output. So this helix over here, cos t sine t t, looks, well, when t equals 0, I suppose we're at x equals 1, y equals 0, z equals 0. And then we kind of spiral around as we're coming up as well. And I suppose we'll only go over to from 0 to pi, but we would keep going up here, and then we take just, say, this portion of the curve. We're traversing that direction. So these are our inputs. I have kind of an output at each of these inputs. If I were to try to draw this analogously to my previous picture, this would be a 4-dimensional picture. 3 dimensions for the inputs, and then 1 other dimension for the outputs. So the kind of analogy to area and painting and so on maybe doesn't make quite as much sense here. But I do have this curve. It's still a 1-dimensional curve, right? If I'm standing on the curve, I can only go forwards or backwards. I can't go left or right or up or down. I can't move off of the curve. It's still a 1-dimensional structure. So our basic ideas are still the same. What's different about it? Well, not very much, really. I mean, instead of f of x of t, y of t, we have f of x of t, y of t, z of t. Instead of root x prime squared plus y prime squared, we just have an extra plus z prime squared. Right. This idea generalizes, this notation generalizes, very nicely to 3 input dimensions or even more if we wanted. So this, we're not really, there's nothing that we've really done in the development of this idea of a line integral of a scalar function that really ties us to 2 dimensions in any way, other than it's just much easier to visualize and to picture if we have 2 input dimensions and 1 output. But if we have 3 input dimensions and 1 output dimension, or even more input dimensions and 1 output dimension, everything is qualitatively the same. We just have to make minor adjustments. And we can see how to make those adjustments just by looking at this form over here, the more vectorized form. Okay, so I want to integrate with respect to t. So t going from 0 to pi. X plus y plus z, these are my x, y, and z for my parameterization of my path. ds, well, remember, ds is like length r prime dt. Or so I have, let me come off to the side here. I have r equals cos t sine t t. R prime then is negative sine t cos t 1. And length r prime is, nicely enough, just the number square root of 2. We get sine squared plus cos squared, that makes a 1, and then plus 1 from the third component makes 2 under the radical. So this is just square root of 2 dt. Right? Most of the time, for most parameterizations, you're going to get something under this radical that's a function of t, but again, we're introducing concepts in chapter 16, we want to focus more on the vector calc stuff and less on the nitty gritty of if I have some nasty integrand, how do I actually go ahead and integrate it? So we're kind of choosing problems that where the integration isn't the difficult part, and it's really the understanding how to set everything up, what the different how the different components come into play, why each of the different components are there, and so on. That's much more what we're interested in at this point. But this just gives me, I suppose, a root 2 in front, and then integrating cos of t to sine of t, sine of t to minus cos t, and then t to 1/2 t squared from 0 to pi. So this gives me root 2 times sine of pi is 0 minus cos of pi. Well, cos of pi is -1, so that's a +1 plus pi squared over 2. And then subtracting off sine of 0 is 0. Cos of 0 is 1. So subtracting off a minus cos of 0. So it's minus a minus is a plus. Cos of 0 is another +1. And then the 1/2 t squared gives me, at 0 gives me 0. So it gives me, I think, 2 root 2 plus root 2 pi squared over 2. Or I suppose we can make that a pi squared over root 2 if we wanted to. Okay, so bumping up to 3 dimensions, 3 dimensions input and 1 dimension output, basically the same thing, but again, just a little harder to visualize. We can visualize the input space, but we can't, really visualize the whole thing like we could up here. All right, so then moving on to our next topic, I told you 16.2 was a pretty big section. So now we're moving into vector line integrals. What's the idea here? Well, the idea here is that I want to integrate over some closed curve, something like this. Maybe I'll put this in kind of quotes because the way I've written it here isn't quite right. This is the idea that I want to do, right? I want to swap out my scalar function f that takes multiple inputs, 2 or 3 inputs, and yields a single output. I want to swap that out for a vector function where I'm now kind of integrating over a vector field. I have a function big F that takes, in this case, maybe 2 inputs and gives 2 outputs. Well, I guess I have a little bit of an issue here that I can't really just integrate vector times some kind of like ds kind of deal. I need to do something else over here. I need to do something with this to, really just to make all of the details work out right. So I think the way that that's maybe most natural to go about this is through an application. Let's think about an application, particularly work, how force relates to work. And let's kind of start at the beginning and work our way up and then see where that naturally leads us. So from back in, very basic physics, high school physics, we have work is force times distance. That's not a dot product dot, that's just a times, just a regular old times. So here, force is constant and distance is constant. Force is constant, and importantly, we're in 1D, so the force is kind of in the same direction as the distance. We're only dealing with 1 dimension, so there's nowhere else the force can be, pointed. It's pointed in the same direction as the distance or the displacement. We just have work equals force times distance. We say how many newtons of force over what length of distance or displacement. That's our work. Now, what if I have force it being variable, but still in 1D? So force and displacement are still pointing in the same direction, but maybe sometimes I'm pushing harder on the box and sometimes I'm not pushing quite as hard, right? I still have a box, say, moving in this direction, and the force being applied is in that same direction, but maybe the force is variable. Sometimes we push a little harder, sometimes a little lighter. Well, now we say that work is the integral of force dx. And what's the idea here? Well, I take the application of that force over the whole distance. I chop it up into a bunch of little tiny distances. Over each little tiny distance, the force is approximately constant over that one dimension. So I'm kind of approximately up here for each of the little tiny chunks. Then I add them together, I take a limit, that turns into an integral. So work is like integral of force dx, kind of d the increment of displacement. Now, what if I have force is constant, but now I'm in 2 dimensions? Well, now things get a little bit more complicated because let's again say that I have a box sitting on a floor here. As I push the box along, it's going to go this direction. That's my displacement vector. My force, it might be lined up perfectly with that displacement vector. So kind of all of the force is, in a sense, contributing to moving the box along. But quite often I'll have a force vector that's kind of in a different direction. So like kind of some of the force is being, in a sense, wasted and just pulling against gravity and not really getting anywhere. And some of the force is being kind of useful in moving the box along. Well, if I have an angle theta here, I know that this force, the component of the force in the direction d, maybe I'll call this fx, the magnitude of the force in that direction d, which here is parallel to the x-axis, is like fx equals length f cos theta. Right, cosine is adjacent over hypotenuse, and hypotenuse is length f. So if I'm pulling at this, angle theta with amount of force length f, that should be length vector f, then only this much of that force is kind of in the, maybe in some sense, like useful direction along d. But force is still constant, so this is like I'm pushing with force length f cos theta in that one-dimensional direction. So I'm kind of like up here, but I just don't get to use all of the force. I only get to use some of it. So here my work looks like length f cos theta, and then times length d, that's kind of the distance that I move over, the length of that vector. But if I have 2 vectors who have their lengths multiplied and then times the cosine of the angle between them, but that's just f dot product. This is a dot now, d. So when my force is constant, if I'm in 2 dimensions, or maybe even more dimensions at this point, the way I've written it, it doesn't much matter. If I'm in 2 or 3 dimensions and my force vector is pointing in a different direction than the direction the thing is moving, well, I take the dot product. The dot product is kind of like how parallel 2 vectors are. So when they're very parallel, most of the force is contributing to pushing the box along in the path it's going. When they're more perpendicular, most of the forces, in an example like this, maybe being wasted in a sense and just pulling against gravity and not getting anywhere, but only a little bit of the force is helping the box to move along. So in a situation like this, work is really the force vector dot the displacement vector. when force is constant. And what about when force is variable and we're in 2D or 3D or whatever? Work is going to look kind of like the integral of force dot displacement, or force dotted with position. But when we think about position inside of an integral, we think of kind of little increments of position, right? We're taking that same structure. We're saying just take this more complicated path that this box moves along and cut it up into little tiny paths. Basically, on each tiny path, pretend that the force is constant, get a little chunk of contribution to work, approximately add all those up, take a limit, turns into an integral. So we need to integrate force dot d little chunk of displacement. And since we already use d for like our dx or ds or whatever here, d bar is kind of strange to write. So we'll write r as the displacement vector, our kind of position vector. And we're integrating over some path in two-dimensional space or three-dimensional space, whatever. And here, this is actually a dot product coming from this idea up here. Okay, so now what am I kind of thinking of? I'm thinking that if I have two dimensions, I might have a vector field f of xy where I take as input two variables, a point in two dimensions, xy, and I give as output two outputs, the two components of a vector in R2. So maybe I have something like this. Maybe this is my force, and maybe I have some curve over which I'm moving this box. Maybe this force is like a whirlwind or something like that that's pushing in a certain direction, and I'm moving my box in some direction, and I have some work done by the field on the box as I'm moving it along. And it's a little confusing and counterintuitive sometimes. I don't know, I'll leave it to the physicists to kind of explain this, but there's like the work done by the field on the box and the work that you're doing and pushing the box through the field. And so there might be a non-intuitive sign popping out or something, but I think this is as far as we'll take this analogy at this point anyway. Okay, so our theorem down here, let big F, a vector field, be a continuous vector field defined on a smooth curve or path. So like maybe this green vector field up here that's defined along this blue curve that we're interested in, this blue curve C. C is R of t, t going between A and B. Then we say the line integral of F, the vector field along the curve C, is integral of C of F dot dr. There's an extra space in there, I think. Let me get rid of that space. There we go. Integral over C of F dot dr, which we say is the integral from t equals a to b of F of R of t dot R prime of t dt. Or we can say that's F dot the unit tangent vector ds. Right. So let's take a look at this integral. Let's take a look at a certain field with a particle moving in a certain path and compute the work done. And then let's try to, as a result of that, after we do that calculation, let's try to see if we can intuitively answer a couple other questions. Okay, so what do I practically need? Well, I need f written in terms of t, and I need to find r prime of t. Then I need to take their dot product, and then I need to integrate that function of t. So f is y comma negative x, but r is xy, x is cos t, y is sine t. So this is f. F is the vector function sine t comma negative cos t. R is cos t sine t. R prime then is negative sine t cos t. And f dot r prime, this should be vector f, and there's a lot of vectors floating around, so make sure you grab the right vectors. Grab r when you need to and r prime when you need to. Easy to get them those two backwards. But I think everything is looking good. And this gives me negative sine squared t minus cos squared t is just -1. So the work done is this integral. It's the integral from t going from 0 to 2 pi of f of r dot r prime, but all of that just boiled down to just the constant -1 dt. Or that's just -2 pi. So if I look at this vector field, let's draw this vector field and let's draw the path. All right, when x is 0, so along the y-axis, f is just yi. That means that f is only pointing horizontally when x is 0, when we're along the y-axis. And when y is more positive, it points more to the right. And when y is more negative, it points more to the left. When y is 0 and we're on the x-axis, we just have f as negative xj, so the vectors are just pointing up and down vertically. When x is positive, they're pointing down, and when it's more positive, they're pointing more down. And when x is negative, they're pointing up. And at intermediate points, they're kind of like diagonal, like this. So this force field is kind of swirling around, I guess, in a clockwise direction. And then, of course, x equals cos t, y equals sine t is a unit circle. And the way that it's parametrized, we're traversing it in the counterclockwise direction. We're kind of going against, we're moving against the way that the force field is kind of naturally flowing. And that gives us the negative work being done here. Okay, so I hope that this idea of kind of taking work from the very basic side of things to what we had maybe talked about in Calc 2, And then a little bit earlier in this course, and maybe chapter 12, I hope this is a natural extension of those ideas. Or maybe this is, for those of you who have taken a lot of physics, this might be old hat for you. Okay, so let's look at another example, example 5 here. Here we're looking to compute a line integral. But note that here it's written in kind of a different form. It's written in differential form. Integral C, instead of something like integral ds, or like integral f dot dr, we're integrating over a curve e to the z dx plus e to the y dy plus x plus y dz. So if we think of f dot dr, if r is x, y, z, dr is like the vector dx, dy, dz. So I can just kind of just take the first component of f and put a dx after it, and the second component of x, put a dy after it, third component of f, put a dz after it, add those together. And that's really what I mean by this kind of differential notation. So here, really, we can think of f as being the vector e to the z, e to the y, x plus y. It takes as input x, y, z, some point, and gives as output a three-dimensional vector. So this is a vector field in R3. And then what's our curve in R3 that we're interested in? Here, C is a closed curve consisting of straight lines going from 1, 0, 0 to 0, 1, 0. Let me put an arrow indicating the direction as well. From 0, 1, 0 to 0, 0, 1. And from 0, 0, 1 back to 1, 0, 0. So we're kind of in our perspective here, looking down on this little chunk of a plane, this little triangle, from kind of high up in the first octant. This is going counterclockwise. All right, so I want to integrate over this curve, but it's pretty clear that it's not going to be feasible anyway to find a parameterization of this whole curve. Right, I want to try to find some x of t, y of t, z of t that traverses this whole curve as t goes from like 0 to 1 or something like that. But I can make use of a theorem that integral over c, I'm just going to write it this way, integral over c equals integrals over c1 plus integral over c2 and so on, integral over cn, if, in a sense, c1 plus c2 plus cn equals c. So in other words, if I take my curve here, c goes here, here, and back around. That's what c is, but I can split it into maybe 3 different pieces. Maybe I'll call this curve alpha, beta, and gamma. And I see that alpha plus beta plus gamma equals c. So if I traverse alpha, then beta, then gamma, that's traversing the whole curve c. And it's, of course, in the right directions here. That's important that all of the directions are consistent and, between the two curves. Okay, so I can split this into three integrals. Let me start with alpha. Well, I want to go from 1, 0, 0 to 0, 1, 0. I want one to go down to 0. So 1 going down to 0 sounds like 1 minus t for as t goes from 0 to 1. I want 0 to go up to 1. That's like a t. And then z just stays at 0. I just stay in the xy plane, so that third component is just 0. And here 0 less than or equal to t less than or equal to 1. This is just a straight line connecting 1, 0, 0 to 0, 1, 0. So then integral over alpha of f dot dr, or integral over alpha of where's my function up here? Can I get everything on one screen? I think I can. Integral over alpha of e to the z dx plus e to the y dy plus x plus y dz. Well, that's integral t equals 0 to 1. Well, e to the z, so here r is 0, e to the 0 is 1. And then x equals 1 minus t. So dx is negative 1 dt. The dt will come out to the end here. E to the y, that's e to the t, times dy is just dt. So that dt factors out as well. And then plus, well, whatever x plus y is, but then I have dz, but z of t is just 0. So dz is just 0 dt. So I'm integrating e to the t minus 1 dt. From 0 to 1. Or that's e to the t minus t from 0 to 1. What is that? E to the 1 minus 1, and then minus e to the 0, and then plus 0. Or this is e minus 2. I'll leave as an exercise to do beta and gamma. But from beta, I ended up with the integral 0 to 1 of negative e to the 1 minus t plus 1 minus t dt, which was 3 halves minus e. So see if you can come up with that same integral and result. And for curve gamma, I ended up getting integral 0 to 1 of e to the 1 minus t dt, which is negative 3 halves plus e. So for my first curve, the bit in the xy plane, the curve alpha, I got e minus 2. For my second in the yz plane, 3 halves minus e. And then from the third, negative 3 halves plus e. So my integral over the whole curve is the sum of these, or e minus e plus e gives me a net 1e. And the 3 halves minus 3 halves, that goes away, minus 2 for my whole integral. And so again, here, just because everything was already in differential notation, I just noted that dr is dx, dy, dt, and that is negative dt, dt, 0. Right. That's essentially what I did here. If you want, one more step in there to help with these other ones. Okay, so that finishes up most of 16.2. Again, I think I'm going to throw in an extra example or so, maybe on gravity or something like that. But that wraps up the main ideas in 16.2. And now we're moving on to 16.3, fundamental theorem for line integrals. So we have a theorem. Let C be a smooth curve given by vector r, t going between a and b, and let scalar f be a differentiable function whose gradient vector is continuous on C. So recall that grad f, if f was, say, a function of two variables, grad f is a vector that takes, for instance, two variables as inputs and gives two values as outputs. Well, grad f, that's the gradient vector field. So this is a vector field. This is an integral that's like this one up here. It's like these vector line integrals, like the work kind of idea, not so much like the scalar line integrals. It's a little tricky because, we see little f here and we think scalar, but remember, we're taking the gradient of little f. So we're integrating a vector field, and I can't seem to select the thing that I want here, but we're integrating a vector field dot d vector r. So the integral over our curve, grad f dot dr, is just f of r of b minus f of r of a. Right? R is like x comma y, so this is kind of like f of x comma y at a, or sorry, at b, minus f of x comma y at a. I think we can see the clear analog to just our basic fundamental theorem of calculus, right? That if we're integrating a derivative, we can just take the difference of the values at the endpoints. Now, interestingly, if we're just taking the difference of values at endpoints, if I have, say, a two-dimensional curve, well, if I'm just taking the difference of the values of the endpoints as the answer, is the integral dependent on the path then? Well, no, the answer is no, it's obviously independent of the path if I only care about the endpoints. If all that's coming into play is the value of f at the terminal endpoint and the value of f at the initial endpoint, then whatever path I take to get there should yield the same answer. So this idea of path independence does come up and is an important idea. Okay, so to that end, let's discuss conservative vector fields. So we have a theorem. And your book, I think, splits this into two or maybe even three kind of different theorems, but I'd kind of wrap them under a single theorem here. And we're doing this in two dimensions, two inputs and two outputs. If we're given a vector field, f of xy equals p of xyi plus q of xyj, if that's a conservative vector field, where P and Q have continuous first order partials on D on some domain. Then throughout that domain, we have the partial of P with respect to Y equals the partial of Q with respect to X. So P gets, P is kind of in the X component and it gets the Y derivative. Q is kind of in the Y component, it gets the X derivative. Well, if big F is the gradient of some little f, then P should look like little f x, right? Because it's in the X component, and Q should look like little f y. So then Py should be little f xy, and Qx should be little f, well, as long as the partials work out nicely, this is also little f xy. Right, the order of the partials doesn't matter under some reasonable conditions. So that's why this is true. And we have this theorem, this part of the theorem, let f be p of xyi plus q of xyj. Let it be a vector field on some region D. And suppose that this condition for the partials holds, then f is conservative. So let's take a look at these fields down here and try to determine whether they're conservative. And then if they are conservative, let's try to find their potential function. Let's try to find their little f that they're the gradient of, right? In single variable calculus, when I want to use fundamental theorem of calculus, I look at my integrand and I say, do I know a function whose derivative is this integrand? What I'm looking at here is basically saying, do I know a function whose gradient is this vector field? Do I know a function whose gradient vector field is this vector field? That's the correspondence. Okay, so this one we saw last time. We actually know this one is conservative because we started with a potential function and took its gradient. But let's see if we could reverse engineer that. Instead of saying, you know, I just had to guess the potential function and figure out that this was its gradient, can I do it in a more systematic way? Well, let's first check. I have the x component is 2x and the y component is y. So P and Q, P being the x component, Q being the y component. And remember, if this is grad little f, then P should be equal to little fx, and Q should be little fy. So I want to take the kind of other derivatives and then check and see if they're equal. So I want to check Py, and I want to check Qx. Py, if this is a gradient vector field, would be like fxy, and Qx would be like fyx. And the equality of mixed partials, those should be equal under reasonable conditions. So what is Py? Well, that's the partial with respect to y of 2x, that's 0. What is Qx? Also 0. These are equal. This should be a gradient vector field. This should be the gradient of some little f. How do I find little f aside from just guessing? Well, I can actually use this knowledge now, right? I know that little f's x partial has to be 2x, and little f's y partial has to be y. And there's a couple strategies you can use here, but I like a strategy that's a little more linear. So what I'll do is I'll take one of these. Okay, I know the partial with respect to x is 2x. Well, that tells me that f of x and y has to be something like x squared, right? If I take the antiderivative of 2x, that gives me x squared. And then I shouldn't forget plus a constant. But one thing I have to be a little bit careful of here is when I say a constant, well, in single variable calculus, it was clear what that meant. It just meant a number, not a variable. But here I'm dealing with the partial derivative with respect to x. I kind of integrated with respect to x, holding y constant. So in this case, a constant could be a number, but it also could be something with y's in it. So I'll say something like g of y. Right, if I take the partial of this blue function with respect to x, then g of y gets knocked to 0, and then I get a 2x, and I get exactly what I expect over here. Now, what some people will do is they'll do the same process with fy and then kind of try to match the two and pair pieces off. I actually like doing it this way better. That now I can look and I can say, okay, what is fy from my blue function? Well, fy, the partial with respect to y, the x squared differentiates to 0. And then plus, well, the derivative with respect to y of g of y is just the regular derivative of g prime of y. So I'm kind of building up my model of what I think little f looks like. The x information tells me it looks like x squared plus g of y. But this also has to parse with the y information. So on one hand, from my model, fy equals, well, just g prime of y. But on the other hand, from my problem, fy has to equal y. Well, now I know that g prime of y equals y. So, so g of y has got to be 1/2 y squared plus an actual constant in this case, which is just actually a number. So g of y has to be 1/2 y squared plus c, which tells me that f of xy has to be x squared plus 1/2 y squared plus some c, where c now is actually just a number. And we can check that if we take the x partial, we get 2x. If we take the y partial, we get y, as we expected. So this is the little f that gives rise to this vector field when we take its gradient. And we can then use that up here, right? This would be the little f that we would be interested in evaluating if we were doing an integral. Now, again, we're not going to quite have time to actually use this and kind of bring the whole topic home, but that should be a short little couple exercises in a supplement. Okay, let's look at B. So again, I have kind of an x component and a y component from my vector field. So this is what I call P and Q. And if this is grad F, for some little f, this would be fx comma fy. So again, P, if this works out, it might not work out, but if it works out, P would be like fx, Q would be like fy. So I'm interested in knowing, does px, or sorry, does py, looking at fx, does py, which is fxy, is that equal to qx, which is fxy, again, so long as the function is nice enough that the mixed partials are equivalent. So I want to know, is py equal qx? So the partial of p with respect to y is just 2x. The partial of q with respect to x is also 2x. And these are equal. So I should be able to find a little f for which this big F of xy is the gradient vector field for that little f. All right, so on one hand, I have that fx equals 2xy. And on the other hand, I have that fy equals x squared minus y. Fx equals 2xy means that f of x and y has to be x squared y, integrating with respect to x. The 2x integrates up to an x squared, and the y is just a constant that comes along, plus a constant, which remember, constant in x means it could be a number or it could be y. It's just some function g of y. And let's do it the other way this time. It's not the way that I particularly like to do it, but just to show the other method. So the y information, we could evaluate that separately. If we integrate with respect to y, we get x squared y, just constant, integrates the constant times y, minus 1/2 y squared, and then plus, let's say, h of x. Well, I see that now when I pair things off, I see that x squared y is in both of them. I see that g of y has to be minus 1/2 y squared. And I see that h of x, well, I guess just has to be 0. So my f of xy equals x squared y minus 1/2 y squared, and then plus 0. And I suppose we could throw on a plus c here if we wanted to. I'll probably forget to do that sometimes, but our end goal is to use this as something like an antiderivative to evaluate something like a definite integral. So the c's are going to, the actual constant c's are going to subtract off when we actually use this. And then we can check fx. Well, the minus 1/2 y squared plus c all differentiates off, and I get 2xy. That looks good. Fy, the plus c goes away. I get x squared minus y. That looks right. Okay, part C. So here again, if big F, which is 1 over y in the x component and x over y squared in the y component, if that's the gradient of some little f, then the first component should be the x partial and the second component the y partial. We call those P and Q. I'm interested in whether the mixed partials are equal, the quote mixed partials, the maybe mixed partials. So P kind of already has an x derivative, it needs to pick up a y derivative. Q already has a y, it needs an x derivative. And if this is a gradient vector field, then this should give us two mixed partials, and they should be the same. So what's Py? It's negative 1 over y squared, just y to the minus 1. What is Qx? Well, Qx is positive 1 over y squared. I mean, they're close, but they are not equal to one another. I'm not going to be able to find a little f for which this is a gradient vector field. And so, so this is not a conservative vector field. I'm not going to be able to use my nice little fundamental theorem for line integrals up here. I might have to integrate, you know, the way that I did in the previous section. Okay, two more. So here again, I have a vector field. I want to know, is this the gradient vector field of some little f? I call this P, I call this Q. If this is grad little f, this would be fx and fy. I like to do this each time because I think it's a little confusing to remember that you want to take the y partial of the x component and the x partial of the y component. But I like to do this just to keep everything straight. So I know that P already kind of has an x partial. I want to find Py and Qx, see if they're the same. Py gives me negative e to the x sine y, and Qx gives me negative e to the x sine y. these are equal, so this is a conservative vector field, and I can find my little f. I know little fx is e to the x cos y, and fy, negative e to the x sine y. Fx tells me that f of xy has to be e to the x cos y, right? When I take the x partial, that gives me this, plus some function of y. Could have y's in it, could have constants in it, just cannot have x's in it. And then fy, well, the e to the x just comes along. Cos y differentiates to negative sine y plus g prime of y. On one hand, for my kind of model to this point, that's what fy has to be. On the other hand, it has to be just e to the negative e to the x sine y. So I see that g prime of y is 0. G of y is just a regular old constant, just a number. So f of xy equals e to the x cos y plus constant. We don't get anything substantive out of that g of y. All right, and for our last bit here, our last kind of example, what about this function? Since we only have a couple minutes left, here's p, here's q. Py is actually equal to qx if you take the derivatives. As an exercise, you can check this. So we kind of feel like saying, oh, okay, well, this is a conservative vector field. Therefore, there's got to be a little f, blah, blah, blah. What's the implication of that? The implication of that is that the value of a line integral over some curve C is just the value of little f at the kind of initial point minus, or sorry, the terminal point minus the value of little f at the initial point. But what if I take a closed curve? If I take a closed curve, let's say the unit circle, then its initial point and its terminal point are the same. Well, it should be true then. And again, we'll talk a little more about this. This is kind of leading into the next bit. If I have a closed curve, the initial and terminal points have to be the same, which means their difference is 0. So if I take the integral over a closed curve of a conservative vector field, well, that should always be 0. But if you actually do this integral, it turns out to be 1, which obviously is not 0. So what went wrong here? Well, we're being a little bit careless when we're going through here, right? Note that it's an important part of the theorem that these criteria have to hold throughout some domain D. Well, what happens at 0, 0? This over x squared plus y squared, well, things blow up, right? This criterion does not hold at 0, 0. So it actually is important that that we're checking these the equality of these partials, and really, keeping in the back of our minds that there are some extra criteria that we have to meet here. Keeping in the back of our minds that we want to make sure that these functions and these partials and so on are well enough behaved over the curve or the region that we're interested in. That is an important thing to kind of keep in mind. So letter E here is more just kind of a cautionary tale that we don't want to be so quick just to take derivatives and check and see that they're equal and then write our answer down. we have to think just a little bit more. Sometimes this can be a temptation even in single variable calculus using fundamental theorem of calculus. When you're going, when you're integrating over an interval where somewhere in that interval, the integrand has a problem, it's discontinuous or something, but maybe you don't see that at the endpoints and you can easily be led astray that way. Similar kind of thing can happen here. So we just have to be a little bit careful and check all of our conditions. But that finishes up our discussion for today. And again, we're going to kind of see this in action in the supplement. It should be a fairly short supplement. And then another supplement that'll be a more full-size supplement on Green's theorem coming up in the next day or so.